Okay, so I'm very happy that Tom actually volunteered to present for us his recent work about mask in the mirror, about implicit sparsification. He's working in CISPA, and I find it one of the finest institutions currently on the territory of Germany. So Tom is interested in understanding neural networks training and making it efficient, therefore sparsification. And he was previously in Eindhoven University, right? And
Yes.
now he's doing his PhD with Rebecca Burkholz, who is also doing brilliant work. So I'm super curious to see the presentation. Thank you very much.
Yes. Yeah, thank you for the introduction, Lina. So this work is called Mask in the Mirror Implicit Sparsification, and together with my supervisor, Rebecca Burkholz, and recently published at iClear. So first some background on sparsification, so why we actually are interested in this in the first place. Neural networks or large language models have become larger and larger and larger, and this is also a big driver behind their success. So a lot of parameters are redundant, or we are significantly over-parameterized. So we want to find ways to turn these parameters off while keeping the generalization performance or for specific tasks. And so there's two main applications to sparsification, namely efficiency and learning structures. So efficiency, one can think of decreasing the inference time or speeding up the actual training process, so the pre-training process perhaps in LLMs. And the other application would be learning structures, so finding which weights will be active on which part of the data, for example. And so this question, there's a question that goes before this, namely, do we actually need all these parameters? And this question has been answered like a while back by Frankel and Carbon, that there actually exists these like subnetworks or like sparser networks that can actually represent the same representation as a dense network and still keep the same generalization performance. So this sets the stage, and so the main challenge then will be how we actually can actually find these networks, or how do we find them by training. And so there's two main approaches, one of which is continuous sparsification and the other one is iterative sparsification. And in this work, we will focus on continuous sparsification. So they can be characterized in the following ways. Namely, continuous sparsification wants to gradually sparsify, so at each optimization step, so think of gradient descent or Adam or some other optimizer, one wants to nudge the optimization process to keep weights small or induce some penalty to keep induce sparsity. While iterative sparsification does something different, namely it does normal training. So take 100 epochs of training with SGD, then it prunes according to some criterion, normally something like weight magnitude. So it removes the smallest weights after a particular period, then starts training again, so just normal training, and repeats this process. This process is normally very long, but can be more accurate, like empirically. And continuous sparsification just does 100 epochs while nudging the optimization process towards sparsity. And the important characteristic which we will use in this work is that they are characterized by so-called reparameterization. And this means we replace each weight of the neural network by a function or multiple parameters. And with this reparameterization, we can actually, turns out, control the sparsity. First we'll sketch the setting into which we do this type of analysis, so this studying these reparameterizations. Next, I will introduce what these reparameterizations do, and then characterize how they control this implicit regularization. And this implicit regularization will then be used again to actually induce this sparsity. And the tool to control this implicit regularization is, in this case, weight decay with shown later that it also can be done with other types of regularizers. So yes, so the setting. So we consider the general optimization setting where we want to minimize some objective depending on parameters x. And we want to just minimize this with, say, plain gradient descent, where eta is learning rate. And we go one step further, namely we consider a setting where the learning rate is super small. And taking this learning rate super small, one can study this problem as an ordinary differential equation, or in other words, a gradient flow. And we can do this because for small learning rates, so in this figure, one can see the trajectories of a gradient flow and a gradient descent. And for the same initialization, we reach a similar type of solution on the solution set. And therefore, we can construct can use the analysis of the gradient flow to make predictions for what will happen in the gradient descent setting or in the more practical setting. Note there is this approximation holds mostly for small learning rates. So in practice, we would use large learning rates, and there will be noise and all these type of factors, and these would play a role as well. But still, we can make predictions using this gradient flow for constructing algorithms. So now I will introduce these reparameterizations that we will later on use to induce this sparsity. So again, we consider this objective f, but now instead of training with a gradient flow, we actually train with respect to a reparameterization, say g, and we take the derivative with respect to the parameters of the reparameterization. So this can be multiple parameters. And for some specific parameters that we in this work consider, one can characterize this dynamics again with a different type of flow, namely a so-called mirror flow. And we use this type of analysis to show or construct then this sparsity bias. Yes, so the particular reparameterization that we consider is the so-called product parameterization. So we replace every weight with two weights and take the product. And then this dynamics can be described by a system of gradient flows. And now we can see that the W drops out if you take the gradient with respect to M, and the vice versa for the W parameter. And then intuitively can imagine if W and M are very small, then this dynamic slows down because the gradients become smaller due to the multiplicative factor in front of the gradients. So there will be some tendency in this dynamics to stay near zero if both of these parameters would be small. And we can formalize this then using this mirror flow. And that's what we will introduce next. So now this implicit regularization can be, in this case, characterized by this type of mirror flows. So to give some more intuition behind what mirror flow actually means, we can draw the equivalence between what the difference is with gradient flow. So mirror flow is actually a strict generalization of gradient flow. Namely, we have some distance generator, which we can refer to as a Bregman function. And in the gradient flow setting, this is the Euclidean distance. And the Bregman function would just be a standard, think of it as a strongly convex function. And one takes steps in this new distance. So now the dynamics becomes this new description with respect to a mirror, with respect to the gradient of this Bregman function. And one particular characterization, this is not necessarily needed for the general mirror flow, but is particular to these reparameterizations, is that the mirror map that you always get is centered around initialization, which is, we'll see later, crucial for neural networks or like for this algorithm design, namely that if we want to induce sparsity, actually we need this mirror to be centered near zero because we want to minimize in the L1 distance and not with respect to the initialization. So we need to somehow be able to move the initialization towards 0 in some sense, in one particular sense, which we will use eventually weight decay for, as we will see later. And to highlight that the difference between gradient flow and mirror flow, we can actually see this now with the same example as before. Now, if we start with the same initialization, the mirror flow actually prefers a weight sparser solution. Namely, it maximizes the first parameter while minimizing the second parameter. So one can actually use these mirror flows to induce sparsity with some levers. And in this product setting, so with this M and W parameter, the mirror map actually depends also on another factor, namely the scale. As I said before about this dynamical system, if one of them is very, or if both of them very small, then we have a tendency to stay near 0. So this is formally characterized as if we are initialized at 0 and the W value is very small, so small scale, then we are, this Bregman function is close to L1, so we are staying very sparse. While if W is actually very large, we're actually back in the L2 setting, so we would not be sparsifying. So this would perhaps lead to overfitting, similar to if one does not use this overparameterization. And so now we're ready to actually use this mirror flow or this overparameterization to actually induce sparsity. So for this, we need to solve two main challenges, namely the initialization is actually not 0 in a neural network. So with some way, we have to move this initialization towards 0, or this the center of the Bregman function, we have to move it towards 0. And actually, we also need to have it to be exponentially small. And this we will do first by integrating weight decay in this formalism. And secondly, we will then use this to induce gradual continuous sparsification. So now one has now a different objective. We add a penalty term with weight decay, and this weight decay will be time dependent, since we find out that in this result that the total amount of implicit regularization applied is the integral over the weight decay strength. So, and as you can see as well, it also depends on the initialization. So this U0 and V0, and it is exponentially dependent on the weight decay. So we can exponentially move it exponentially fast towards 0. So in addition, we want to, yes, perhaps it's better to highlight it in the figure. So this formula, what does it actually do? So consider we initialize at 1, so then we have the Bregman function is centered at 1 and is roughly an L2 shape. But then if we start adding more and more regularization, we actually move the minimum towards 0 and the shape starts changing towards L1. So this is very beneficial for sparse training, as we might want an L2 bias in the start and an L1 bias in the end, since we want to stay sparse at the end of training. And interestingly, we can then also more or less turn off the weight decay while keeping the benefits, since this function has changed in a lasting way. Yes, so this is the algorithm. And there's two main innovations, namely we can now use dynamic weight decay to use some target sparsity. And we also initialize unbalanced. So you can see this M0 squared minus W0 squared is beta is strictly larger than 0. This is necessary to be able to move through 0. So as one can see in the previous slide, if this A depends on U0 and V0, and if M and W are the exact same value, this A is 0. So this restricts the domain of the Bregman function, and therefore one actually cannot move through 0, which might hamper performance because we are artificially restricting the parameters to either the positive or negative half. And so this is the first innovation. And the second one, or the second innovation, and the first one is that we can turn off the regularization in the end safely while we keep the benefits of the implicit regularization. So to highlight this second sign flip constraint is that if we take a balanced initialization, so when this beta is 0, we get back a previous algorithm developed, which is called spread. But then for linear regression, if we initialize with the wrong signs of the weights, so the x has the different sign as the ground truth, then one cannot move through 0, and actually we can not reach close to the ground truth in the end. So one can see that the blue line stays, doesn't converge at all, well, both just lasso, so x with L1 penalty actually gets close to the ground truth, while pilot, so with the correct regularization, so pilot is our algorithm, referring to the implicit regularization, and this actually reaches the ground truth perfectly due to being able to sign flip and then also turning off the regularization in the end. Okay. So we verify this algorithm or compare this algorithm with other contained sparsifications, such as the previously mentioned method spread, and another method based on soft thresholding, which is based on proximal operators, and is also based on reparameterizing the neural network with this operator. And we outperform all of these methods with some margin on C410 and C400. And similarly, we also do the same experimental ImageNet for ResNet50, and we see mainly in the high sparsity regime. So for for high sparsity, like around 95%, we see larger improvements, while we are somewhat competitive in the 80% sparsity regime. And in addition, finally, we also combine it with these other sparsification methods, so these iterative sparsification methods, and we also improve then over these methods, so learning rate rewinding and weight rewinding. And so learning rate rewinding just means that we prune and then just train again. And weight rewinding is actually that we will reset the weights to the value of the warm-up. So one actually does not keep the weights at the same level. But both of these methods get improved by using pilot on top of it. So the main takeaway is we can use this implicit regularization framework to actually induce sparsity gradually and improve performance by actually turning weight decay off in the end and making sure that we can sign flip during the training. And so I want to thank my supervisor, and also my work can be found on my website, and there's a QR code for seeing the paper.